Hello and welcome to Deeksha Karnataka YouTube channel, and today I am going to discuss the chapter electric charges and field, but with a twist that we are going to discuss this chapter within 20 minutes, so it will be a rapid fire revision. So if you have already completed the chapter and you want to revise the concept quickly before your exams are coming, so that's why I have decided to do a chapter within 20 minutes. And if you want the remaining chapter to be done like that, then you have to comment in the comment section below, so that we get the encouragement to do all the chapters for your physics, right? So we are basically starting with electric charges and fields, and let us discuss what are all the concepts that we are going to discuss in today's rapid fire session. Electric charges and properties of charge. We will also discuss Coulomb's law, electric field and field lines, electric dipole and dipole moment, and electric flux and Gauss's law. So entire chapter will be covered today in just 20 minutes. So stay with me till the chapter is over, and if you want to revise it quickly, definitely it will be very helpful for all of you. So first we will start with electric charge. Okay, so when we are talking about electric charge, you have to remember few things, that there are two types of charges. One is positive charge, one is negative charge, right? Now, what is the meaning of positive and negative charge? We will see that as well. Now, like charges repel each other and unlike charges attract each other. Okay, if the charges are same in nature, they basically repel. If the charges are opposite in nature, they attract each other. In neutral object, positive and negative charges are balanced, so they are equal. So if I say that neutral object, sir, give me one example of neutral object. Neutral object is you, me, this TV. So they are all neutral object because they are they do not have any excess charge. Otherwise, if you have touched it, you should have get electrocuted. That means they do not have any excess charge. To charge a neutral object, we need to add or remove electrons. Electrons are negatively charged, so only electrons can be added or removed to charge an object. Okay, if electrons are added to a body, it gets negatively charged. If the electrons are removed, the body becomes positively charged. Okay, so if you are adding the electron, it becomes negatively charged. If you are removing the electron, the body becomes positively charged. So imbalance of charges. Now, how can we measure the charge? The gold leaf electroscope is a device that can measure the presence of charge. So if an object is charged or not, if the object is positively charged or negatively charged, everything can be determined using gold leaf electroscope. SI unit of charge is Coulomb, and its dimension is A into T. A is dimension of current, T is dimension of time, right? Now let's move on. Basic properties of electric charge, very important concept. There are three basic properties. Charges are additive in nature. What is the meaning of that? Charges can be added algebraically. Algebraically means the way you have done in your algebra in your lower classes. 2 minus 1 is 1. Okay, 2 minus 3 is minus 1. So same way you can add charges. Okay, so for example, q minus 2q plus 3q is equals to 2q. No vector addition because charges are scalar quantity, right? So normally when you are talking about charges, you have to assume that the charge is a scalar quantity. They are actually a scalar quantity. Charges are conserved. Okay, total charge of an isolated body is constant. Total charge of an isolated system is always conserved. Conserved means constant. Okay, it will not change if the system remains isolated. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created or destroyed. So as I give you many times, I have told you the example. So suppose we have plus 10q and we have minus 20q. So net charge is minus 10. Okay, now you can increase this charge by 10, you can decrease this charge by minus 10, but total charge should always remain minus 10. Okay, you can create or destroy, so charge always appear in pairs. Okay, so positive and negative charge. If you create or destroy there are ways to create and destroy charges, but even if it happens, the net charge of the object remains same. Okay, charges are quantized. Very important. Quantized means they have a fixed minimum possible value. Okay, all free charges are integer multiple of a basic value of charge denoted by small e. Okay, so this is the smallest possible charge. Any charge which are there in the nature, they always have to be integer multiple, 2 times, 3 times, 5 times, 10 times. It is not possible to have a charge which is say 10.5 times. That is not possible. Okay, only integer multiples are allowed, decimal multiples are not allowed. Okay, and the net charge of an object can be represented by q is equal to any, n can go from 0 to any integer value. E is the charge of an electron and the value is 1.6 into 10 to the power of minus 19 Coulomb. Now if you want to practice for your KCET exam, then ABHYAS KCET 2026 test series is already live. Here you are going to get 35 tests, 4 of them are free and 31 is paid. To get the free tests, you have to register yourself in the link given in the description section of this video. Also you will get chapter wise KCET 10-year PYQs for absolutely free of cost. You don't need to pay anything, just you pay the price for the test series and you will get this for absolutely free. Okay, real KCET exam pattern and timing. So if you want to practice the timing for your KCET, which is 60 questions within 60 minutes, so that practice can happen through our ABHYAS test series. So if you are still waiting, you are still wondering, don't wait anymore, just click on the link given in the description section of this video and register yourself today. Now let's continue with our discussion. Next is very important concept, Coulomb's law. For PU exam, this question based on Coulomb's law question came every year. Okay, statement: the force acting between 2 point charges is given by directly proportional to product of the magnitude of the charges and inversely proportional to the square of the distance between the charges. Okay, so we all know this. The force acts along the line joining the two charges, and mathematically the same formula can be written as F is equal to K Q1 Q2 by R square. K is Coulomb constant, which is given by 1 by 4 pi epsilon naught. The constant is very simple to remember, 9 into 10 to the power of 9 Newton meter square per Coulomb square, where epsilon naught is called permittivity of free space. So permittivity means how much permission it will give, okay, to the electric field to exist inside it. So that value for free space is 8.854 into 10 to the power of minus 12 SI unit. You don't need to remember this value. If you are facing a question based on this, the value will generally be provided in the question, but this value will not be provided, so you have to remember this value. Okay, also in your PU board exam, sometimes they might ask in vector notation. So in vector notation, the vector r cap is essential and you have to write the formula as F is equal to 1 by 4 pi epsilon naught Q1 Q2 upon r square into r cap. Okay, so this is plus F, and the other force, this is F vector and this is minus F vector. You have to draw this diagram compulsorily. So if they ask you to write the Coulomb's law in vector form, along with this the diagram is compulsory and the explanation of the terms are also compulsory. Now let's move on. Electric field. So now Coulomb's law basically talks about two charges, right? Two charges, force between two charges, attraction or repulsion, whatever is there. But what about one charge is present, another charge is removed? In that case, what will be the effect of this charge at this point? So is there any effect present or not? Yes, there is a effect present, and that effect is denoted by something called electric field, which is a vector quantity, and electric field is given by E equals to 1 by 4 pi epsilon naught Q by R square R cap. Now R cap generally I am taking here because I am assuming the charge is positive. If the charge is negative, the R cap will be in the opposite direction. Okay, because there is a negative sign over here, so minus R cap anyway will represent negative vector. Okay, so E basically 1 by 4 pi epsilon naught Q by R square. It is the electric field vector. Q is called source charge, small q is test charge. Test charge is not there anyway. If a test charge small q is kept inside an electric field, then the force experienced by the charge is q into E. Now you know only electric field, you do not know anything about the source charge. So suppose this electric field is known, and you place a charge, then there will be a force acting on this charge. Okay, so this force is given by Q into E. We need to know a little bit more about this force. The electric field due to a system of charge exists at every point in three-dimensional space. So everywhere electric field is there. For a positive charge, the electric field will be directed radially outward from the charge. Now remember, these are not properties of electric field lines, they are just property of electric field. For a negative charge, the electric field vector at each point points radially inward. So if the charge is positive, electric field is outward. If the charge is negative, electric field is inward. Okay, so this is very basic point to remember. Now what else? Electric field due to a point charge is spherically symmetric. Spherically symmetric means if the charge is point, then if you draw concentric spheres, electric field will be constant on the surface of this sphere. A positive charge experiences a force in the direction of the electric field. So if you keep the charge positive, so I gave you one example, electric field, and if you keep a charge, if the charge is positive, it experiences a force in the direction of electric field. If the charge is negative, it experiences a force in the opposite direction of the electric field. Now let's move on, properties of electric field lines. So this is an important question as well in your PU exam and in your KCET exam. Based on these properties, many MCQs have come. Field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. So if the charge is positive or negative, based on the nature of the charges, electric field lines will always start at positive and end at negative. In case one charge, it can start or end at infinity as well. In a charge-free region, electric field lines can be taken to be a continuous curves without any breaks. So for example, if there is no charge present, the line is continuous. Okay, so line is not like that. This is called line with breaks. So this is not the way to draw electric field lines. Electric field lines has to be continuous curves. Okay, so remember this. What else? Two field lines can never cross each other. If they did, the field at the point of intersection will not have a unique direction, which is absurd. So electric field lines can never cross each other. If they did, at this point of intersection, if you draw the tangent that represents the direction of electric field, it will not be unique. There are two possible direction of electric field, which is not possible. Electric field is a vector quantity, so each and every point there is only one direction is allowed. Okay, electrostatic field lines do not form any closed loop. So it is started from positive, it ends at negative, it does not come back from negative to positive. So they are open loops. They are not closed loop, they are open loops. Electric field in free space decreases as we move in the direction of the electric field lines and vice versa. So if you are moving in the direction of electric field lines, the value or magnitude of electric field decreases. So here electric field is high, and as you are moving along the line, this will be low electric field. Clear? Let's move on to electric dipole. Two equal and opposite charges separated by a small distance is known as electric dipole. So here we have plus q and minus q, the distance between them 2a, and that is very small distance in the order of micrometer. Now for a dipole there is a fixed quantity that is called dipole moment. Electric dipole moment is the product of magnitude of one of the charges and the distance between them is a vector quantity. So if you multiply any one of the charge and the distance between the charges, that is called dipole moment, and it is a vector quantity. The direction is given from negative charge to positive charge. So the dipole moment is directed from negative charge to positive charge. Okay, n cap is a unit vector in the direction of the dipole moment. The direction of the dipole moment is from negative to positive. Let's move on. Dipole moment along the axis of a dipole. Now along the axis of the dipole, the derivation is important for your PUC. I have done the derivation in our Brahmastra series. If you want, you can go and check that out. So now this is a negative charge, this is a positive charge. If you try to find the electric field along the axis, this is called the axis of the dipole. So the line which joins the charges and extended, it is called the axis of the dipole, and electric field along the axis of a dipole is given by 1 by 4 pi epsilon epsilon naught 2p by r cube. As you can see, it is a vector notation. So in vector notation means electric field and the dipole moment both are in the same direction. Okay. So if you are considering electric field due to a dipole, electric field due to a dipole along the axis is basically in the same direction. And for points on the equatorial plane, if you try to find the this is called if you bisect the distance between the dipole and construct a plane, then that is called equatorial plane. And on the equatorial plane, electric field is given by 1 by 4 pi epsilon naught p by r cube. Magnitude wise, equatorial plane is actually half of the electric field on the axial plane. Okay, so axial plane and equatorial plane is related like this for magnitude. Okay, even in the direction is also opposite. So if you see that electric field is in this direction, dipole moment is actually in the opposite direction. That's why there is a negative sign. The negative sign represents electric field and the dipole moment, they are in the opposite direction. Formula is very simple, and both of them are proportional to 1 upon r cube. Normally electric field is proportional to 1 upon r square, but for a dipole they are proportional to 1 upon r cube. Now let's move on. Dipole in external electric field. Now so far we are discussing about dipole moment on the electric field due to the dipole. Now if you keep the same dipole in an external electric field, what happens is that the dipole experiences a torque, and the expression for the torque is Pe sine theta. Okay, or P cross E. So this is very handy. The derivation is also important. Again, I have done it in our Brahmastra series. You can go and check that out. Last concept of the day, Gauss's law and its application. So before going into Gauss's law, electric flux is, you have to remember, electric flux is basically if you have a surface and some field lines crossing it, then if you take a perpendicular, whatever angle is theta, and if you can understand that how much field line is passing through the surface normally, then that measurement is given by electric flux, which is given by E dot ds, okay, or E dot delta s. Okay, so E delta s cos theta is called electric flux. This is the general formula for electric flux, but Gauss's law gives a more measured approach for electric flux. Electric flux through a closed surface, remember this, electric flux through a closed surface. This law is not valid for open surface. Electric flux through a closed surface is given by phi equals to q by epsilon naught. Now phi can be represented by this. So if you take the integration, you get the total flux. Okay, so to calculate the total flux, this is delta phi, means small amount of flux. So to calculate the total flux, you have to integrate it, and integration E dot ds equals to q by epsilon naught. Q is the total charge enclosed by the surface S. Few points about Gauss's law. Gauss's law is true for any closed surface, no matter what is the shape and size. Very straightforward. Here small q includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface, no specific location such as center of the charge, but it is located anywhere. Electric field is due to all the charges, but small q is only for charge inside. So suppose we have some charges q1, q2 and some charge q3, q4. So electric field, when we are saying that electric field E dot ds, electric field is because of all the charges. Okay, so if I say electric field is E over here, electric field is due to all the charges, but the term q by epsilon naught, this q is only the charge which is enclosed, that is these two charges. Okay, the surface that we choose for the application of Gauss's law is called Gaussian surface. Gauss's law is often useful to calculate the electric field for symmetric surface, but Gauss's law is applicable to any surface, but it is useful for symmetric surface because of the integration. Okay, now we have a few application of Gauss's law. Field due to an infinitely long straight wire is given by 1 by 4 pi epsilon naught 2 lambda by r. Because I have used 1 by 4 pi epsilon naught, that's why I am written it 2 lambda by r. So if you see that electric field for a straight wire is proportional to 1 upon r. What else? Field due to an uniformly charged infinitely conducting sheet. For conducting sheet, electric field is given by sigma by 2 epsilon naught. This is an infinite sheet, okay? So E is equal to sigma by 2 epsilon naught. So it is a independent of distance, independent, only depends on the charge density, surface charge density. So charge per unit area, that is called surface charge density. So it is only dependent on surface charge density and not depend on distance. What else? Electric field due to a uniformly charged spherical shell. So spherical shell is something which has material only on the outer edge, inside is hollow. So if you charge this shell, the electric field outside the shell is given by 1 by 4 pi epsilon naught q by r square. So q is the charge on the shell. So this is same as electric field due to a point charge, with a twist that inside the shell electric field is 0. So if you go inside the shell, electric field is 0. If you plot the graph, it will be looking like this. So here it is 0, here it is decreasing upon 1 by r square. Okay, so this is the end of this lecture, and if you want more quick fire rapid revision, don't forget to mention that in the comment. I'll be back with more lectures very soon. Till then, bye.